Okay, Calc BC, Unit 3, Day 5, Office Hours, book assignment. Most of the problems are out of your current orange textbook. I did assign one from the last one. You can see the link for those pages from the last assignment. There is no assignment for no day 4, skip day 4. So 23, maximizing profits. Suppose that Rx, which we're assuming represents revenue, cost equals 2x squared. X is measured thousands of units, so X is thousands of units. Is there a production level that maximizes profit? If so, what is it? So we're looking for X to maximize profits. So that's kind of a summary of the information that you have. We should probably come up with a profit function, which is revenue minus cost. And so then we could say, okay, well, that's going to be 8 squared of x minus 2x squared. And we're going to take the derivative of it. So I'm just really taking kind of like extreme value optimization kind of approach to this. So it's going to be 4 over the square root of x minus 4x. Might be good to combine these into a single fraction. Equals 0 undefined. Find critical points. So x can't be 0. X equals 0 is a critical point. And then the top, 4 equals 4 x to 3 halves. 1 equals x to 3 halves. We would raise both sides to the 2/3 power. 2/3 gives you x equals 1. So that's your critical point. Now, in my solutions, on some of these problems, I show second derivative tests, which you're welcome to do if you want. I guess x equals 0 is a critical point too. Not a very exciting one, since you're making nothing. Extreme value theorem doesn't necessarily work here. I mean, you could try and make a little table and say, all right, let's put 0 in, let's put 1 in, and then let's take the limit as x goes to infinity. If you plug 0 in, you get 0 profit. Makes sense. Plug 1 in, you get 6. If you go to infinity, this is a dominant term. It's going to go to negative infinity. You're going to lose lots of money. So you could say right here, okay, well, this is clearly the max. Now, justifying that's a little hard. On, say, a free response problem, you'd have to kind of explain your limit stuff here. Otherwise, you could try first derivative test, which is also a little difficult to justify. First derivative test, put the critical points on there, test a value, x equals 2 into p prime. Plug 2 of this. 8 times square root 2 is definitely bigger than 4. It's going to be negative. Negative, positive, negative. It's down, up, down. Doesn't really make sense to consider that, but so there we have relative max, and then it's got to be the absolute max. If we enforce, that we have to produce positive units of the actual amount. So we could say the maximum profit is let's see, what's the money stand for? 6. Is it thousands of dollars also? Cost x is measured in thousands of units. Yeah, I don't know. I thought Well, yeah. If x is thousands of units, and if you put 6,000, um, no, if you put 1,000 in here, that's gonna be 8,000 minus 2,000, or I don't know. Profit is 8x squared minus 2x squared. So if you plug 1 in, you get 6. And that's 6,000. So, because x is thousands. So maximum profit is $6,000 when producing 1,000 units. Now, that doesn't have justification, but I'm going to skip that part right now. I showed you guys in the notes. So I'm not going to write that the same kind of phrases down and stuff. I'll let you guys do that. I'll probably ask for you to do it on the test. You probably have like one problem like this on the test, your next test, which is a little ways away. 24 says, suppose that Rx equals x squared over x squared plus 1. Cost equals x minus 1 to the third over 3 minus 1/3. Thousands of units. Production level maximizes profit. So it's kind of the same kind of question. We want to maximize profits. So profits equal revenue minus cost. So x squared over x squared plus 1 minus x minus 1 to the third over 3 plus 1/3, because you have to distribute that subtraction. So that's your profit. And then so we'd find P prime, and this would be quotient low D high minus high D low all over low squared. This is going to be x minus 1 squared. So we should probably try and clean this up. This one's pretty ugly. So 2x cubed plus 2x minus 2x cubed. I mean, let's see what I did here. Yeah, this is x squared minus 2x plus 1. Now these cancel, and then we could give these all least common denominator. But on the top, we're going to need to actually multiply it through by and multiply it all out. So this is ugly. So what are we going to get? 2x positive 2x minus x to the sixth minus 2x to the fourth minus x squared plus 2x to the fifth plus 4x cubed plus 2x minus x to the fourth minus 2x squared minus 1. Oh my gosh. So I'm gonna cave on this problem and end up just using my calculator at some point. We could write it a little nicer, maybe kind of like standard form or something. So let's see, we have a negative x to the sixth and x to the fifth plus 2x to the fifth, x to the fourth minus 3x to the fourth, x to the third plus 4x to the third, x squared minus 3x squared, x is plus 4x minus 1. I mean, this is ridiculous. So I'm going to say equals 0 and define and solve it. So I'm going to do this on my calculator. Let's see if I can pull this off my calculator. Parentheses negative x to the sixth plus 2x to the fifth minus 3x to the fourth plus 4x to the third minus 3x squared plus 4x minus 1 divided by parentheses x squared plus 1 close squared close window, probably looking at positive values, and we're looking for where this I guess specifically we could just look at the top and the bottom. Undefined x squared equals -1 squared to both sides plus or minus. I'm not going to take those, so really it's just the top. So go back here, I can get rid of this division stuff. I don't really need the parentheses. Okay, and window, I just care about the x-intercepts. So now you might try this. There looks like there was something right over there. Well, and I don't really see anything. Window, I'll just jump to it. Okay. I don't know if did I make any mistakes here. Yeah, well, I'm not seeing it, so I'm getting stuck on this one. I thought I pulled off. Okay, for. There's definitely one early on. We can go window, or we go send count 0 and say, well, let's look for 1, 0 to 10, guess 1. And there's one that's like early on, I think. X equals 0.2941075. And then the other one, I don't know, second calc, we could just try and look for it. Say, well, let's look from 100 to 2000 and guess. Oh, I didn't like that. Put in 2000. Didn't I? Oh. I meant to put 2000. So the other one's way later on, and I wasn't seeing it because I was making the graph big enough. Or maybe not. I don't even see it now. You could just try it, but yeah, this is not working great here. Okay, so let's see. Oh, just make this graph a lot smaller. Maybe we can see what's going on. Yeah. Yep, there it is. I was making the graph too big because I was thinking thousands, but these aren't thousands yet. So second count 0. There it is. 1 to 2. Guess 1.5. The other one is 1.5251083. Okay, there. Yeah, pulling around there. Okay, p prime of x. We could try first derivative test, even though we have multiple critical points. This one from the bottom, well, that's not anything. So we could test. I mean, you just look at this graph and you'd be like, okay, well, it's positive here, negative here, negative here. It's decreasing, increasing, decreasing. So this is a relative max, and this is a relative min. But we're going to stop at 0 units, and then this goes forever. So we could test. If you plug 0 in to your profit function, you get 0. So I'm kind of doing like first. I'm kind of doing extreme value theorem. So what's the profit at 0? It's 0. So what's the profit at 1.525, 108? It's this is crazy. Let's see. This is pretty tough. 1.525, 108. I don't even want to do this. And I miss my decimal point. Okay. Can I store this? Watch. Let's do a trick here. Store an alpha. We're going to store an A. So then I don't have to retype it anymore. So if I do this, let's see. Alpha A squared plus 1 times 2 alpha A minus alpha A squared times 2 alpha A divided by parentheses alpha A squared plus 1 close squared close, and then I'm doing the wrong one. Okay. All right. So this is what I get. 0.984403. So this is relative max. It's the absolute max. This is not a great justification. We're going to say the maximum profit is, you're going to multiply this by 1,000. So $984 when producing 1,525.108 units. So there you go. Let's see, 25 says to minimize the average cost. They give you a cost function. And so average cost is going to be total cost divided by x. Okay, and so then we want to minimize this. So take a derivative, say equals 0 and define. Get critical points at x equals 5. We don't really have endpoints other than 0. X should be greater than or equals 0. So we just have one critical point, so we could just jump right into first derivative test. We could plug 0 in. It's negative, positive, decreasing, increasing, relative min, absolute min, right? So the minimum average cost is, you plug 5 in there, 0. Well, no, average cost here, 25. 25 minus 50 is negative 20, negative $55. That's when producing $55,000 when producing 5,000 units. It seems weird, but it's like what it is. All right. We have another minimizing average cost problem. So 26 cost is x e the x minus 2x squared. So we could look for average cost. Average cost, take derivative of it. Say equals 0 and define. Solve it. So this is the critical point. There's only one. We could do first derivative test. Natural log 2 is definitely positive. Right? Definitely positive. Test a. I'm just saying that because it's definitely to the right of 0. Test, say x equals 0. E to 0 is 1. And this is negative. This is positive, decreasing, increasing. Relative min, absolute min. So when we say the minimum average cost is, plug natural log of 2 in here, you get 2 minus 2 natural log of $2 times this one also thousands times thousands of dollars when producing natural log of 2 times 1,000 units. I'm not putting justification in there. That's what I got so far. '18's a little review problem from previous assignments. So piece of cardboard measures 10 by 15 inches. 10 by 15 inches. 2 equal squares are removed from the corners of a 10-inch side. 2 equal squares from a 10-inch side. 2 equal rectangles are removed from the other corners so that the tabs can be folded and form a rectangle of the box with a lid. So they're saying they're going to do this. So what it's going to do is it's going to fold up here, and then this is going to be the lid. So that's our plan. It says Two wheel workers. Okay, so they kind of lead you through the steps here. A, write a formula for the volume of the box. I'm going to call these little cuts X, 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 X. And then this lid should be equal to the base so that it closes nicely. So we got to figure out, okay, well, if the height is X over here and X, then we got to take two X's away, and then we got to divide them by 2 because this one's going to get half of that also, right? And then this is going to be 10 minus 2X. So the volume is going to be X times 10 minus 2X times 15 minus 2X over 2, right? Now we could divide the 2 into this, right? Makes it a little nicer. Probably should go ahead and multiply it out. So that's going to be 5x minus x squared, 15 minus 2x. Keep going, FOIL it. 75x minus 10x squared minus 15x squared plus 2x cubed. And combine like terms, write in standard form. 2x cubed first minus 25x squared plus 75x. Okay, so that's your volume formula. So that's all they wanted you to do in part A. They said part A, just write a formula for the volume. Okay. Part B, find the domain of V for the problem situation and graph V over this domain. Okay, so we're going to graph V, but we got to figure out the domain. So the domain is like the endpoint. So X definitely has to be bigger than 0. And the biggest X would be 5, right? Because that's when the two corners would meet each other. So that's our domain. And, you could write it different ways. We're going to graph it. So we're going to do 2x to the third minus 25x squared plus 75x. Window 0 to 5. We'll just graph on the domain. We could do zoom fit. Pre-calculates it, resizes the window to fit all the y values for your x. So quick sketch. Looks like that. And it says, okay, part C, use a graphical method to determine the absolute max. So here's the max. So I'm going to use my graphing calculator, I guess. So I can calculate maximum. This is 0 to 5. It looks like it's around 2. So maybe say 1 to 3, guess 2. And it is 1.9618732, comma 66.019118. So we're actually trying. This is part C. We're trying to find the maximum. So the maximum. We're going for maximum volume. The maximum volume is 66.019. The units are inches cubed when the cut. Did they tell us to use X? The cut X equals 1.961 inches. So something like that. D says confirm your result in part C analytically. So that means like do extreme value theorem or something like that. So we're going to try it. Let's see if we can get it. So V prime is 6x squared minus 50x plus 75. We set it equals 0 undefined. we can't divide anything out. We could use quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. So it's going to be 150, 300, 1800, 1800. So it's going to be square root of 700. So that's going to be 50 plus or minus 10 square root of. So we could take a 2 out, a 25 plus or minus 5 root 7 over 6. But we don't want we don't want the negative one. So this would be the same thing as this would be a large. This is larger. Well, square root of 7 is like 2 point something. So I mean, let's see. Let's just put these in our calculator. 25 plus 5 square root 7 divided by 6. So that's one of the answers. And the other answer is 25 minus 5 square root 7 divided by 6. 1.961873. Okay, so these are critical points, and we could make a table. We're not going to consider that one because it's outside the endpoints. Right? And we're plugging this into volume. Okay. Now, if you plug 0 in, you get 0. If you plug 5 in, you're also going to get 0. So we just got to figure out what that value is. So I could store it alpha A, and then we could do 2 parentheses alpha A raised to the third power minus 25 parentheses alpha A squared close parentheses plus 75. No, that doesn't seem right. Let's make sure I'm plugging in the right thing. Where's the original volume formula? 2 plus 75. Oh, okay. I missed the last one. Plus 75 times alpha A. There we go. So that's 66.019118. So that's your max, right? Here's your mins. So I'm going to say the maximum volume is 66.019 inches cubed when the cut x equals 1.961 inches. Same answer that we got from just looking at the graph. Technically, we'd say by extreme value theorem. Checking endpoints and critical points. Okay. And then we had one problem from the other book, page 350, problem 44. So we were doing problems already from page 350 on assignment 3. So you should be able to use that. It says a firm determines that X units of product can be sold daily at P dollars per unit. P dollars per unit. And X is number of units. It says where X equals 1,000 minus P minus the price. So the cost of producing X units per day is, so they give you cost. Okay. So part A says to find the revenue function, Rx. So revenue is price times quantity, right? Price times number of units. Okay, now I'm assuming we want to get it all in terms of like one variable. So we come up here and we could solve for price. Price is 1,000 minus X is another way of writing it. So we could say, well, revenue is 1,000 minus X times X. Or we could simplify it and say it's 1,000 X minus X squared. So there you go. That's A. B says find the profit function. Okay, well, profit function is revenue minus cost. And so we just got revenue. Revenue is 1,000 X minus X squared. And cost, they gave us earlier, was 3,000 plus 20X. So then we could simplify this, distribute the subtraction. We could say, okay, well, this is going to be, negative X squared. It's 1,000X minus 20X would be 980X minus 3,000. So that looks good. Profit function. Part C says, assuming that production capacity is at most 500 units per day, determine how many units a company must produce to sell each day to maximize the profit. So here's the nice thing about this is they actually give us a cap. So X, first of all, we can't make negative units. We could make 0, but it says we can only go up to 500. So these are your endpoints. So we can now do extreme value theorem. Okay. So we're going to determine how many units we must produce and sell each day to maximize profit. So we're going to take a derivative, negative 2x plus 980 equals 0 undefined. So x equals 490 is your critical point. We're going to make a table and plug this into profit. We're trying to maximize profit. So we're going to do 0, 490, and 500. So we plug 0 in here. We're at, if you plug 0 in yet, negative 3,000 for profits means you're losing a lot of money, right? Okay. We could just plug these in, I guess, real quick. Negative 2, parentheses, 490. Oh, no. Let's see. Negative parentheses, 490 squared plus 980 parentheses, 490 minus 3,000. So that's going to be 24,3100. Let me make sure I did that right. This last one I think is supposed to be minus 3,000. Okay, sorry, that's wrong. 23,710. So I'm going to do the same thing with 500. So I'm going to copy and paste. I just think this one would be quicker. And this one is 23,700. Oh my gosh, that's close. So here's your max profits. This is your min, losing lots of money, which is realistic. So, so this is where it happens. Part D asks, find the maximum profit. Part E says, what price per unit must be charged to obtain the maximum profit. So let's start with, we're going to answer C and D. We're going to say the maximum profit is this is dollars, when 490 units are produced and sold each day by extreme value theorem. Checking in points and critical points. Okay, good answer, good justification. Very good. Now E says, what price per unit must be charged to obtain the maximum profit? Okay, so we were told earlier that the price, we were told earlier that X equals 1,000 minus price. So then we realized that profit equals 1,000, or P stands for price, by the way. It's 1,000 minus X. For us, that's going to be 1,000 minus 490. So the price is going to equal $510 per unit. There you go. All done. Some tough, heavy problems.